we're now thinking about how we can compute slope for a function of two variables in an arbitrary direction. So previously, when we had a function of two variables, here's a function where we have the level curves of the function drawn in the xy plane, and if we go to a particular point, we know that if we move in the x direction, we can learn the slope of the function with respect to x, the partial of f with respect to x, evaluated at the point P. And in addition, we can learn the slope of the function with respect to y, the partial of f with respect to y at point P. We now have the notation to think about arbitrary directions, not just directions along the x-axis or along the y-axis. So if I go to my point P, I can draw in a vector in an arbitrary direction, and I'm just going to let that vector be a unit vector. So that means that if I go a radius of 1 unit out from point P, any vector that I draw is going to have its tip on that circle. Considering this arbitrary direction, I can now ask the question, what is the instantaneous rate of change of my function if I move in this direction that's not one of the axial directions? One way to identify this slope is to consider what happens if we move a distance h along this direction. We can see how much the function changes when we move a distance h, and then we can make h smaller and smaller and smaller, taking a limit to get that instantaneous change along this direction. Our arbitrary direction is u1i plus u2j. Recall that we've chosen this to be a unit vector, and we want to move a distance h, and so to move a distance h along this vector direction, we need to move by the vector h times u. This vector will have length h. This new vector is hu1 in the I direction plus hu2 in the j direction. hu1 plus hu2, we're moving a small distance along this vector direction. When we move that distance, we go from a function value of f of ab, the value of the function at our original point, to a function value of f evaluated a plus hu1, comma b plus hu2. So we're taking the function value at the new point and subtracting from it the function value at the old point to learn how the value of the function has changed. And then to get the slope, we divide by the distance that we moved, and we moved out a distance h in this vector direction. Using local linearity, we can approximate the value of the function at a small distance from f of a comma b, and that's because h is going to be small. We want to take the limit as h goes to 0, so let's just approximate this using a locally linear approximation. The value of the function is approximately equal to the value of the function at the original point plus the slope in the x direction, so the rate that the function changes in the x direction, times the distance we're moving along that I component, plus the rate that the function is changing in the y direction, times the distance that we're moving along that j component, and this gives us an approximate new value for the function when we move over h1 and up h2, and this approximation becomes closer and closer to exact the smaller h is. This means that the difference between the value of the function at the new point and the value of the function at the old point is approximately equal to the partial with respect to x times the distance in the x plus the partial with respect to y times the displacement distance in y. To find the approximate slope, we divide the difference in the function by the distance that we traveled, and we find f sub x of ab times u1 plus f sub y of ab times u2, where u1 was the I component and u2 was the j component of the unit vector that was giving us our direction. And this approximation becomes more and more exact in the limit as h goes to 0. So in that limit, this is actually an exact expression for the slope of the function as we move in the arbitrary direction given by u1 and u2. To denote the derivative in this arbitrary direction, we use the notation f sub u, where u is the direction of interest and the magnitude of u is equal to 1 at the point AB, and this is equal to the partial of f with respect to x at AB times the I component plus the partial of f with respect to y at AB times the j component of the vector. This derivative in an arbitrary direction u is called the directional derivative of the function. We can rewrite this expression using dot product notation. So this directional derivative, which is a weighted sum of the partial of f with respect to x weighted by the I component of our direction plus the partial of f with respect to y weighted by the j component, can be rewritten in this format as the dot product of our direction vector and the partial of f with respect to x, I, plus the partial of f with respect to y, j. This vector gets the special name the gradient vector for f of xy.